Hello and welcome to another one of D's ADD videos. Today we're going to be looking at the concept of alkyne reactions. If you remember, alkynes are triple bonds, and the ones we're going to be concerned with are terminal alkynes, meaning the triple bonds located at the end of a carbon chain. Okay, this R right here can be any type of carbon chain that you can imagine. And basically, we need this hydrogen right here, okay? This hydrogen is what's referred to as an acetylenic hydrogen. And when you react it with sodium amide, what you create is this very electron-rich species, this acetylide ion. And the sodium is not important. What we are concerned with is this electron-rich species that has those nucleophilic properties that can do things like backside attacks and react with carbonyl groups or primary alkyl halides. A lot of the reactions you saw for alkenes are also going to occur. Okay, so if we were looking at the Wade textbook, just looking through briefly, the nomenclature is always going to be the same pretty much as what you did for alkenes, except for it's an -ine. So as always, we put the location of the triple bond directly in front of the suffix -ine. Now for precedence, who takes precedence? Well, hydroxyl groups have precedence over the triple bond. Okay, notice the alcohol suffix is at 2 versus the triple bond that's occurring. However, halogens come after the triple bond, meaning the triple bond takes precedence over halogens. So that's why halogens has a higher coefficient than the triple bond. Keep in mind the sum rules, where the sum of the direction you choose must be the smallest. That was the nomenclature. Again, this is the acetylenic hydrogen. That's the important thing there. Internal alkynes aren't as reactive. We're looking at selected alkynes and their melting points and boiling points. You can go through all that on your own. So here is electron density, and you can see as we increase in the number of bonds, the bond distance gets shorter, making this a very compact bond relative to an alkane. And here's your different views of your acetyl. No, actually, this is of the terminal alkyne. So when we look at the overall acidities, you can see that the alkyne here has a pK of roughly 25. Okay. Weaker acids like acetic acids are 4.5, but these do have some acidic character to them. So what can occur given the right reagent is you can turn this alkyne into something that will donate that proton. And the thing that we're going to use is that sodium amide that we discussed earlier. So here's a terminal alkyne, there's the acetylenic proton, and it gets dislodged and the amide group comes in, and then you get this ionic bond right here. Okay? So again, the sodium goes away, we don't care about that. Byproduct is ammonia, we don't care about that. What we care about is the fact that we have this very electron-rich species tagging along this whatever R group we want it to be. So here we have no acetylenic protons. They therefore will not react with the sodium amide. So just a little bit more on how we can make the sodium amide. It's a little bit of detail you don't need. Let's see. This will be the next video. when we discuss the first set of reactions, which consists of the nucleophilic attack of a primary alkyl halide. All right. So I hope I've clarified any confusion you might have over the basics of alkynes and given you enough confidence to start looking at these problems and practicing these problems. We're going to go through all these different reactions that alkynes undergo. So make sure you check out all the different example videos. Practice, practice, practice. Thank you and have a nice day.